Hello everyone, this is Manas, your friend and tutor. And guys, today's session is going to be all about thermal stresses and strain. Now this is going to be very important for both civil as well as mechanical engineering students. First of all, with the help of a very simple illustration, I'm going to be explaining you how these sort of temperature stresses or thermal stresses are set up. So let's see how that works out. So I'm going to be taking two cases. Case number one. And this case basically talks about the free expansion of a steel rod, let's say. So guys, just take a look at this example. Let's say we've got a steel rod whose one end is fixed, okay, while the other end is free. And let's say this end over here is fixed. This over here is a steel rod. And let's just say that the steel rod is having a length L. What happens if the temperature rises? Let's say initially the temperature is T1 and the temperature changes or rises from T1 to T2, right? So let's say T is the change in temperature, or you can also say this as the increase in temperature. What will happen to the length of the steel rod whenever there is an increase in temperature? Remember, by facts, it's an established fact that the change in length, if there is going to be an increase in temperature, then there is going to be an increase in length. Now, when this is given a temperature rise, let's say T is the increase in temperature, then the length would increase by a certain amount. And this is the free expansion. This over here is basically represented by delta L. And this delta L is nothing but alpha into T into L. Now, some of you guys might be wondering as to what alpha is. Let me tell you, alpha is the coefficient of linear expansion. Okay, remember this. Let me write it over here. Alpha is the coefficient of linear expansion. Now, this steel rod was allowed to expand freely. Okay, and if you allow this to happen, then obviously the increase in length is going to be equal to alpha TL. But what we are really interested in is the thermal stress. Now remember one thing, whenever you talk about any material which is allowed to expand freely, no stresses will be generated, no stresses will be set up or induced. Once again, if the material is allowed to expand freely, then no thermal stresses will be developed. Remember. Secondly, let's talk about case 2. And case 2 is going to be very interesting. Let me tell you why. Because in case 2, we are not going to allow the steel rod to expand. So just take a look at this case. This is going to be really interesting. Here the arrangement is such that no expansion takes place. There is a temperature rise, but no expansion takes place. So the arrangement is going to be, there is going to be a support at the left, and there is also going to be a support towards the right hand side. Let me just show you. Okay. Now this again is a steel rod and the length is, the original length is N. Let's say this is given a rise in temperature of T. Well, by the way, T is equal to what? T2 minus T1. Secondly, the coefficient of linear expansion is represented by alpha. Now guys, just think about this. What will happen? If this is given a temperature rise, the natural property, the characteristic, the inherent property of the material is such that it will always try to expand. If you increase the temperature, there is going to be an expansion. If you decrease the temperature, there is going to be contraction or reduction in length. Let's say for this example, we've taken the increase in temperature case. That means increase in length. But these supports are such that they are preventing the expansion, isn't it? So let me just write this. Supports are preventing expansion. Now guys, watch this carefully. What if I remove this, or rather if I had to substitute this with a force, can that be done? Okay, watch this carefully. This is very, very interesting. If I were to replace this, this support, let's say this is support at B and this is support at A, there must be some kind of compressive force acting which is preventing this rod to expand further. Okay. Now, if there was no force, then this would have expanded, isn't it? Had there been no support, then this would have expanded by an amount of delta L, and we know that delta L is equal to alpha TL from here, free expansion case. But we also know that due to this support B at B, there obviously is going to be some force acting over here, and let's say that the force is denoted by P, capital P. And because of this force, or rather this force prevents this steel rod to expand by an amount of delta L. Now if I were to say you that can you get me the value of strain? So the strain in this case is going to be the extension prevented. Let me just write this: extension prevented divided by the original length. Extension prevented with respect to the original length. Now let's see how this works out. Here, strain in this particular case is the ratio of extension prevented with respect to the original length. How much extension has been prevented? This much extension. This much extension has been prevented, whose magnitude is what? Delta L is equal to alpha TL, isn't it? So the extension prevented is alpha TL with respect to the original length. How much is the original length? Well, that is L. This is L, isn't it? So that's L. So these two fellows are going to cancel out, and the stuff remaining is E is equal to alpha into T. And this over here is nothing but a thermal strain. Thermal strain. Well, you can also call this, in this case, you can also call this as a compressive strain. Okay. Now, in the same manner, if you have got the value of strain, you can also find the corresponding stress. How? With the help of Hooke's law. We know from Hooke's law that Young's modulus E is equal to stress over strain, isn't it? Now, if I were to tell you what is the value of strain, strain is going to be equal to stress over E. Now, this is very interesting. E's value is what? Alpha TE. So, this is going to be alpha T is equal to sigma over E. And what we want to find is the stress. So, stress can be worked out. Stress is going to be equal to alpha T into E. And this right over here is the thermal stress. And what is the nature of this thermal stress? The nature of this thermal stress is compressive. Right? So that was all about thermal stresses. Now guys, one more thing which you need to think about. Just listen to this question. If I were to tell, in case of, let's say, increasing the temperature, if we were supposed to decrease the temperature, then what would have happened? There would have been contraction. Okay, and that contraction can also be calculated with the help of this formula, alpha TL. In this case, when the temperature reduced, what would have happened? This material would have tried to contract, but because of this support over here, automatically a force develops. The nature of that force will be towards this right hand side. That means tensile in nature. In that case, you will be saying that the thermal stress developed will be tensile in nature, and this thermal strain will be compressive strain. That's the entire idea. You need to remember two things. One, if the material is allowed to expand freely, this is the formula which you are going to use. Or remember, in case of free expansion is equal to alpha T into L. Remember this. If you want to find the value of strain, the value of strain is actually equal to what? Alpha T. Remember these formulas, and the value of corresponding stress. This is thermal strain and this is thermal stress, is going to be alpha T into E. If you remember these three formulas, I am very much sure that you're going to go ahead and solve whole lot of objective problems and conventional problems based on thermal stress and strain. In the next video, I'll be talking about composite bars or compound bars and what happens to them. I mean, there is a system in which there are two or more materials. What happens in that cases? So we'll be taking a different session on that. For now, let us try to solve a numerical and let us try to implement all of these things which we have learned right now. Okay, here we go. Okay, let me just read the problem for you. Right, I'm sure a lot of you guys who are still watching this video must have read the description. Anyway, so there are rails which are laid such that there is no stress in them at 24 degrees Celsius. That means the initial temperature, right now the temperature is 24 degrees Celsius. Let's write this given. So the initial temperature has been given as T1 has been given as 24 degrees Celsius. Fine. Anything else? If the rails are 32 meter long, length of each rail is 32 meter. Okay. The first thing that we've been asked is to calculate the stress in the rails at 80 degrees Celsius when there is no allowance for expansion. Let me just write this. First part of our solution. Stress at 80 degrees Celsius for no expansion. Just take a look at this. The railway track is something like this. Let's say this is a rail. Okay, and then there is no provision for expansion. This is railway track 1 and this is track 2. Let's say there are two rails attached, right? And there is absolutely no space in between them, which has been clearly said. No expansion or no allowance for expansion. What would happen? Obviously, some stresses are going to develop. What kind of stresses? It will try to expand, but it won't be able to do so. So the kind of stresses which are developed are thermal, and those thermal stresses are of compressive nature. So simply you can apply the formula sigma is equal to alpha T E, and we've also been given the value of alpha and E. Let me just write them. Alpha has been given as 11 into 10 raised to minus 6 per degree Celsius, and the value of Young's modulus, well, this is made up of steel. Young's modulus has been given as 205 gigapascals. So let me just write 205 into 10 raised to 9 pascals. Well, pascals is Newton per meter square. Okay, fine. So there is absolutely no provision for expansion, and this is how much? This is 32 meters. There is absolutely no provision for expansion. So obviously stresses will be induced. So you just have to punch the value. This is 11 into 10 raised to minus 6 multiplied by T. How can T be calculated? Very interesting. So if you watch carefully, this over here, this is the initial temperature 24 degrees Celsius, right? And then this over here is T2. So if I were to calculate the rise in temperature, T is the rise in temperature, will be equal to T2 minus T1. So 80 minus 24 will give you the value as 56 degrees Celsius. So multiplied by 56 multiplied by Young's modulus, well, that is 205 into 10 raised to 9 for gigapascals. So this is per degree Celsius, this is degree Celsius, and this is in Newton per meter square. So obviously once you punch all of this into a calculator, the final value which you are going to get, well, this is going to be equal to, let me just write this, 126,280. 126,280 into 10 raised to 3 pascals. So if you go 3 decimal places back, you will have 10 raised to 6. So this is going to be, let me just write this finally, sigma is equal to 126.28. This is going to be 10 raised to 6. That is mega MPa. Remember, this is the stress calculated when there was no allowance. And this is really a very beautiful problem. And after going through second part, you'll realize this why. Let's do this. Second part. In second part, some kind of allowance is possible. I'll show you what that is talking about. So in between two rails, there is allowance for the steel rail to expand. Let's see that. Okay, where shall I write? Here. Okay, what is the statement? The statement is the stress in the rails at 80 degrees Celsius when there is an expansion allowance of what? 8 mm. So the case is something like this. So there are two rails, one over here, let's say, and the second rail is here, and in between those two rails the allowance is how much? This over here is 8 millimeters. Okay, now this distance is how much? That is 32. That is the length of each rail, you know, rail 1 and this is rail 2. Both of them are, well, they are made up of steels. Now these two rails are actually locked with the help of a steel plate. This plate is something like this, and then it is bolted over here and it is bolted over here also. right? Some kind of a arrangement, this kind of an arrangement is done. And I've also seen rails being made to come in contact with the help of thermit welding also. Do read about thermit welding. Okay. Now, we need to find the stress at 80 degrees Celsius for an expansion allowance of 8 millimeters. So, the rise in temperature is from 24 degrees Celsius to 80 degrees Celsius. So, the rise in temperature is 56 degrees Celsius. That is 80 minus 24. That's for sure. Right? Now, earlier in this particular case, how much expansion was prevented? Just watch. Let me just write the formula. Let us do it in the most general sense. If I were to calculate the value of strain is going to be equal to what? Expansion prevented. Expansion prevented with respect to the original length. Watch this. In the previous case, it was preventing an expansion of alpha TL. Okay, but here it is going to prevent an expansion of alpha TL minus 8. Isn't it? Isn't it right? Right? Remember this. With respect to the original length, how much is it? L. Now we also know that Young's modulus E is equal to what? Stress over strain. Okay, that is E. So if I were to calculate the value of E is going to be equal to what? Sigma over capital E. Isn't it? So E can essentially be replaced by sigma over capital E. So this is exactly how the equation can be framed. Once again, watch this. E is basically the expansion prevented with respect to the original length, right? Isn't it? This is the thermal strain. Now, if rail 1 and rail 2, if there was absolutely no space between rail 1 and rail 2, let's say this is 0, there is no space, then the expansion prevented would have been alpha TL. Done? But right now, there is some provision for this rail 1 to expand. How much is that? That is 8 millimeters. It can first expand 8 millimeters, and after that, if you go beyond that, then only there will be stresses induced or thermal stresses induced. But right now, it is alpha TL minus 8. Okay. So, some reduction in stress is going to take place. So, if I were to tell you, get me the value of thermal stress, you can use this formula. How can that be done? Well, this is going to be very simple. Sigma over E is nothing but 205 into 10 raised to 9. Done. Is equal to, be very careful in putting up the values. Alpha is 11 into 10 raised to minus 6 multiplied by T is 56. Length is how much? That is 32. Done. Newton and meter. We are going to be following newtons everywhere, newtons and meters. This 8 is in millimeters. So you have got to be careful. So minus of 8 into 10 raised to minus 3. And anything else? With respect to the original length, by the way, already has been given in meters. That is 32 meters. Sigma will work out as 7503234. Okay. 4, 5, 6. Yeah. This is Newton per meter square. Now, if I were to convert this into megapascals, this, by the way, Newton per meter square is pascals. I have to convert this. So, stress is equal to what? 1, 2, 3, 4, 5, 6. So, this is going to be equal to 75.03 megapascals. Okay. And this is allowance of 8 mm. And earlier, we had calculated the stress, zero allowance, no allowance. And you can clearly see, initially the value obtained was 126 megapascals. Right now, it's almost half. That is 75 megapascals. Can you understand the reason? Can you understand the reason? The reason is very simple. If you don't allow the steel rails to expand, the thermal stresses are going to be of a higher range. If you allow some expansion to take place, in that case, the thermal stresses would get reduced. That is why you must have seen this railway tracks or the rails connected to each other, consecutive rails are connected with the help of a plate, and there is always some gap kept in between, and that is the allowance. Right? Now you know the answer. Why there is allowance? Allowance is in order to compensate for the expansion taking place in the summer season. Let's say when the temperature is very, very high. Let's see what we are supposed to do in the third part of the problem. Here we go. Let me just read this. In third part, the expansion allowance for no stress. Okay. Now, if you are supposed to ensure that no stress should be induced, no thermal stresses should be set up, in that case, how much expansion? Well, delta L we know very well is equal to, if it is allowed to expand freely, how much is it going to be? Alpha T into E. This is very simple. Alpha we know very well. Not E, this is alpha TL. This is 11 into 10 raised to minus 6. T we know. How much is it for no stress? 56, and L by the way is 32. Okay, so delta L is going to work out as in meters. Well, by the way, this entire answer will work out in meters. Delta L will work out as 0.01971. 0.01971. This is in meters. If I were to convert this into millimeters, this is going to be 19.71 millimeters, which essentially means if you keep an allowance of 19.71 millimeters and let the temperature rise, listen to this very carefully. If you keep an allowance of 19.71, or in other words, if you allow the steel rail to expand up to 19.71 millimeters, maintaining this change in temperature of how much? 56 degrees. The change in or rise in temperature of 56 degrees, then no stresses will be generated. Okay, that's it. And finally, the fourth part of our problem, and this says the maximum temperature for no stress in the rails when expansion allowance is 8 mm. Let me just read this once again. The maximum temperature, how high can we go? The maximum temperature for no stress in the rails. Okay, so the expansion allowance is given. Expansion allowance is 8 millimeters. So delta L has been given to us. How much? 8 millimeters. We cannot go beyond that. Right? So we need to find that maximum temperature, okay, which will help us reach this expansion allowance. This is also very simple. Now delta L you know very well. Delta L is represented by alpha, T and L. And delta L actually has been given as 8 millimeters. So 8 into 10 raised to minus 3. Alpha is 11 into 10 raised to minus 6. So right now the temperature is T1. We have to go to T2. Okay, T1 how much? T1 is 24. We don't know what T2 is. So what can we do? We can write the rise in temperature as T is equal to T2 minus T1, that is 24. So in place of this T over here, this rise in temperature, I can write T2 minus 24 multiplied by length. Now this length also has to be worked out in meters. The length of each rail is 32. So that's 32 for you. So you just do this math. T2 is going to work out as, let me tell you, T2 is going to work out as 46.72 degrees Celsius. 46.72 degrees Celsius. And if you want to find the rise in temperature, that can also be done. T2 minus T1. This is very simple. This is going to work out as 22 point something. What is that something? 22.72 degree Celsius. And guys, in the next session, we'll talk about compound bars, right? A system of copper and say a copper tube and a steel rod and vice versa. We'll be giving a temperature rise to those systems, and we'll be trying to work out how much stresses or thermal stresses are induced. All of that and much more in the upcoming lecture, rather the next lecture. So guys, that was all for today. I'll see you again in the next video. Until then, take care. Have a nice day. Keep learning and keep watching. Thanks.